Welcome back. We are continuing now with our study of the kinematics of continuum mechanics. In the most recent units and in the most recent segments actually, we learned about the deformation gradient. We learned about how the deformation gradient is a fundamental measure of how vectors on this body, right, vectors scribed onto this body are mapped forward by the deformation into their current configuration. Okay? And we also saw that from this fundamental definition of the deformation gradient and its action, we can also learn about the effect on surfaces and volume elements under the deformation. And we saw that in all of these effects, it is the deformation gradient that dictates how things evolve. We're going to continue today with our study of the deformation gradient. We're going to look in particular at how the deformation gradient can also be used to elucidate ideas of strain. And we're going to study these measures of strain. All right? So we're going to look today at, we're going to continue with the deformation gradient, right? So let's just recall one thing about the deformation gradient. Right? We have right, that's how we are denoting the deformation gradient, and it is simply this object. Okay, and in the context of what it does for configurations, we have this picture. We have omega naught, the motion phi carries it to the current configuration, omega sub t, and what we saw was that if we have a vector there, which we denote as x minus y, right? Right? Sorry, so that vector is actually y minus x, the way I've drawn it. So if we have a little vector there, y minus x, we saw that under the deformation, that vector could go to something like that, right? Little x is the deformed position of capital X, little y is the deformed position of capital Y. Okay, and we saw that y minus x equals f acting on y minus x capitalized, the reference positions, plus other terms that are of order y minus x Euclidean norm square. All right, and at the very end of the last segment, we observed that if capital Y minus x were small, right, in the limit that this term is small, we saw that essentially the deformation gradient is a first order measure of the stretching of the fiber between points y and x. Okay, so f is a first order approximation of the stretching of the material fiber y minus x capitalized. Okay, the idea of the material fiber is simply that we could think of scribing a little vector capital Y minus capital X on this reference configuration and look at how that material fiber is stretched by F. Okay? What we're going to do in this segment and the next couple of them is going to be to look at this idea of stretching and really work it out in detail and understand its mathematical and physical implications. All right? Okay. So here's the approach we're going to take. We're essentially going to reproduce that picture that we had on the previous slide. Omega naught, we have omega t phi. Now, instead of drawing a fiber vector here as y minus x, I am going to call it the following, right? I'm going to say that that vector is epsilon times m, right? Where epsilon belongs to, it's just a real number, it's a positive real number, and the vector m, right, m is a vector such that the Euclidean norm of m equals 1. All right, so what this implies, of course, is that epsilon is the magnitude of that vector, right, and m is essentially a direction. Right? But importantly, it's scribed on the material. All right. And now, of course, we're going to look at what happens with this material vector. We know what happens with it under the deformation gradient. It is mapped to a vector that we will denote here as epsilon f acting on m. Okay? So we know how this works. All right. So what we need to do now is try to understand more about this. Here's what we can do. We can ask ourselves, well, if this thing gets mapped forward, let's just calculate the square of the magnitude of the deformed vector. Okay? So we could call it the magnitude, or we could also use the term that I've been using today, which is square of the magnitude, or the Euclidean norm of epsilon m after deformation. Right? So epsilon m has been mapped forward by the deformation, right? Same idea. I have a little vector here, it's been mapped forward by the deformation. What is the magnitude of the deformed vector? Right? Or what's the magnitude square, really? Okay, so we know how to do that straight away, and the way we do that is the following. We have this quantity that we're talking about is simply the following, right? Epsilon f m dotted with itself, right? Okay? Now, what I'm going to do is to write this out using coordinate notation, right? Epsilon is a scalar, so it just comes along for the ride. I'm going to write the first f using indices little I, capital J. For m, I use capital I. We have epsilon again, f, little j, m, capital J. Okay, using coordinate notation. Now we can work this thing out, and actually I see that I made a small error here, so let me just correct it right away. I should have I here. We can rearrange this now by pulling out the scalars, epsilon square, and I'm going to write this as m I f I f I j m j. Okay? Now, observing the arrangement of indices on the first f and on the second f, it should be clear, if you recall the way we defined transposes, it should be clear that what we have here is f transpose, right? We have f transpose capital I, f I j, m j. All right? And now when we put it all back together, going away from coordinate notation, we observe that we essentially have this product here. We have epsilon square, which is a scalar, m dotted with f transpose f acting on m. Okay? That essentially is the square of our original vector epsilon m after being deformed. Now, in the process of doing this, we've introduced a new tensor, or at least we're going to use a new label for it. We're going to henceforth label f transpose f as a tensor C. Okay? Now, what is the effect of C? What C has done is that it has essentially taken the undeformed vector epsilon m. Okay? C acts upon epsilon m, and then after dotting it again from the left by epsilon m, what we see is that, what we observe is that we're left with the square of the magnitude of the deformed vector. Okay? So, what we see is that what this little exercise above implies is that epsilon m dotted with C acting on epsilon m. Okay, let's just remember that that's a vector, that's another vector, is the Euclidean norm squared after deformation. Okay? Another way of saying this is that the effect of C is to give us the square of the stretched vector. Right? So let me just say that. C gives us the square of epsilon m stretched. Of course, I recognize that this very last sentence is somewhat colloquial, right? I'm just trying to convey a more physical sense of what C is doing. Okay, and how does it give us the square of epsilon m stretched? Well, we saw the result on at the end of the previous slide, right? The result at the bottom of it. Okay, that is what we mean by it. Okay, all right. For this reason, C comes with a rather grand name. C is called the right Cauchy-Green tensor, sometimes called the right Cauchy-Green stretch tensor. Cauchy and Green are, of course, mathematicians. Cauchy is perhaps the more famous of the two. We understand why we call it a stretch tensor. The use of the term right there will become clear in a little more as we continue to develop the material. Okay, so C is one of our fundamental measures of the stretching of fiber vectors, right? Of material fiber vectors out here, right? So you take a little fiber vector here. You know what its magnitude is in the reference configuration. It gets deformed by the deformation gradient. It's carried into the current configuration, and C, when it is applied to the original undeformed vector epsilon m, essentially gives us the square of the magnitude of epsilon m after the stretching. Okay? All right. So this you know, as you may observe, what we're doing here is to take the idea of the deformation gradient and make it a little more elaborate, right? We're trying to understand what more it tells us. Now, observe that C gives us a stretch, tells us about the stretching of material fiber vectors. It is not yet a strain, okay? Because the notion of a strain is really a difference, okay, from some original state. So let's try and establish that, okay? That's not too difficult because C already gives us the square of epsilon m after stretching. If we want to think about the difference, all we need to do is to consider, well, what was it like, what was the vector like in its original state? Okay, so to get a notion of strain, we do the following. Okay, and the idea is that this notion of strain is one of difference. Okay, difference from the reference state. Okay, that's easy enough, right? What we need to talk about, what we need to think about is the following. So to get at this notion of strain, let's consider the following, right? Let's consider consider the square of the magnitude of epsilon m post-stretching. Right? We've been seeing this for the past few minutes. Okay, we have that. And now we're just going to subtract out the original square of the magnitude of epsilon m before stretching. Now, we may write that as just epsilon m dotted with epsilon m, but I'm going to do just one more thing, which is I'm going to put in our second order isotropic tensor inside here, right? Because it does nothing. It, after all, is just your identity matrix, right? So you can have that acting on epsilon m. Okay? All right? And this gives us what we wanted, right? It is now the square of the magnitude of epsilon m post-stretching minus the square of the magnitude before stretching. Okay? As one last thing, what we may choose to do here is to actually just divide this thing through by the original magnitude square. Okay? Thereby we get rid of the effect of the original size of epsilon m. Right? So now we're really effectively looking at the idea of strain untainted by the size of the original vector. Okay? And this thing just cancels out all the epsilons. Okay? And so what we're left with is the following object. We're left with m dotted with the right Cauchy-Green tensor minus that acting on m. Okay? Now, what we have here within parentheses already gives us a sense of strain, right? So the idea is that you take a vector in any direction, right? Typically take a unit vector m, as we've done here, have this new tensor sitting in parentheses, that is what we've written as C minus the isotropic tensor. You have it act upon m as shown, and you get effectively a measure of the change in the magnitude of the original vector, right? And we've actually normalized it through by the original magnitude of the vector. Okay? Now, the term in parentheses could itself serve as a fundamental measure of strain for us, right? And so we do, except that it is common. It's common for mainly for notational purposes to also consider 1/2 of this quantity. Okay, it's just a matter of convention. All of continuum mechanics could equally well have been developed without that factor of half in there, but for various reasons which will become clear as we go on, It's mainly for consistency with other descriptions of mechanics that this is done, that we put in a half there. Okay? So, what we have here now is a new tensor, right, that we are going to denote with the letter E, but I will give it a, make it a bold-faced E. Okay? This is our first measure of strain. Okay? It also comes with a name. This is called the Lagrange strain tensor. Okay?